now we want to consider algorithmic aspect. So now we are learning this probabilistic method. Many statements, we prove them using probabilistic method. In combinatorics, lots of time when you actually prove a theorem, that proof can be turned into an algorithm to deal with a specific instance of a problem. But for the probabilistic method proof, you might think that how would it be possible to turn probabilistic argument into an algorithm. But oftentimes it's also possible. So for example, we can consider one instance of how we can actually convert a probabilistic argument into a deterministic algorithm. One example is this method called the method of conditional probability. So this is something that we learned in the undergraduate graph theory. If you took it last year, you must have learned it, but before that you might not. So let me repeat. So one of the most basic statement we have learned is about the Ramsey number, that the RKK is at least 2 to the k over 2. There are some constants here. I need to turn off the internet. Yeah. Anyway, so how did we prove this? How we proved this was we consider a random coloring of H, so of the complete graph on n vertices. And then we just show that with positive probability, there are no monochromatic clique of size k in there. That shows the existence of such coloring. But if you want to actually find one such coloring, how can we do it? We can actually do it with the following way of converting the proof into an algorithm. So we can actually ensure a polynomial time algorithm to color the edges of Kn, so that the number of monochromatic copies of Kk is at most n choose k times 2 to the 1 minus k over k choose 2. So this is the number. This is the expected number of monochromatic Kk in a random H coloring of Kn. So if n is the number that we have proved before, then this number is smaller than 1. So this algorithm guarantees that there are no monochromatic Kk in a coloring which is obtained by the algorithm. And how do we do it? Is we consider a complete graph Kn on vertex set bracket n, and we consider partial to coloring f of edges of Kn. Here, partial to coloring is that some of the edges are colored, but some of the edges are not yet colored. Let's denote the edges of colored edges as a H. So subgraph H is a collection, which consists of the edges which are colored. And what we do is we define the following weight. For each set S, which consists of the K vertices, we let the weight of S be either 0 or 2 to the 1 minus K choose 2 or 2 to the minus K R, where if S is already ruined by F, that means, not ruined, but if already S is good, in a sense that S will never be a monochromatic KK, which means two edges in S choose 2. So there are edge inside which lies inside of this S, which already gets two colors, which are different. And if no edge in there is colored, then this is default weight. And if F colors all but R, which is smaller than K choose 2, edges inside of S using only one color. So this is a weight which seems a bit artificial, and we let weight of F be summation of all weights of K sets for a partial coloring F. So this is certainly a deterministic weight. In order to determine F, this weight of F, for given F, you just consider all possible sets of size S, and then for all of them we just compute this and then we add. This can be even computed in polynomial time, n to the k many choice of S. And then each one of them we can just compute this value. But it is a deterministic weight, but it has a probabilistic interpretation. So probabilistic interpretation is that the F is partial coloring, so some of the edges are colored, but some of the edges are not colored. So for given this partial coloring F, we randomly color the remaining uncolored edges. Then, what's the probability? Probability that S is monochromatic, conditioning on F is already colored, color remaining edges at random. Maybe if you write it this way, it's not conditional probability. So F already colors these edges, and for uncolored one, we randomly color the edges. Then what's the probability that S is monochromatic? If S already has two colors with a different color, then the probability that it's monochromatic is 0. If no edges in here are colored, then the probability that S becomes a monochromatic KK is this. And if F colors all but R edges with one color, say red, then the probability that the remaining ones are all colored by the same color, say red, is 2 to the negative R. So this is exactly weight of S. So this weight of F is exactly nothing but exactly the expectation of, say, x, where, let's write it this way. So let's consider x is the number of monochromatic K clicks in a random coloring pi, random H coloring pi of Kn. So this pi is chosen uniformly at random. So for each H you color it with red or blue, and you condition on the event that this subgraph H, this F has exactly, same. This is exactly same with F. Conditioning on that, what's the number of monochromatic K click? So when, pi is restricted to this edges of H, it's same with F. So, so this is a conditional expectation. So now what we do is we choose on HE not colored by F. Any E is okay. And let F1 and F2 be two extension of F by coloring E with, say, color 1 and 2. So let's name the two colors by 1 and 2. Then, what do we know? Because of this interpretation, this is conditional expectation, and this is exactly half times x when it's restricted with, in here is F1 plus half times same interpretation. So all the events in here, so assuming this we consider here, while assuming this, there are two cases that the E is colored with 1 and E is colored with 2, and we consider the expectation and then we multiply the probability that E is colored with 1 and E is colored with 2, then we get the original expectation. So because of this, what we know? We know that weight of F is half times weight of F1 plus half times weight of F2. This implies that there exists choice of I such that which guarantees this weight is not increasing. So this shows that at least one of these two must be smaller than or equal to the original weight. So now we color E by I, and we repeat. Then what's the weight of empty coloring? Weight of empty coloring is actually this. Weight of empty coloring is expectation of x without conditioning anything. So that's exactly the target that we wanted, which is n choose k times 2 to the 1 minus k choose 2. And also by our choice, this weight always decreases. And once we finish the coloring, then what's the weight? Weight here is that this case is 0. This case doesn't happen at the end. This case never happened. And this case, if R is 0, then this is 1. So in that case, it just counts the number of monochromatic alkali. So weight of F is number of monochromatic K clicks when F is a coloring, not the partial coloring, but the full coloring of edges of Kn. So in the end, because of this choice of ours, in the end we obtain a coloring with less than this many. K clicks. And also every time we have to decide which one to choose, whether I as 1 or 2. For that we have to actually compute this weight of F1 and F2. Two cases we have to compute. But in order to compare which one is bigger, there is E, and then we have to just consider the older set of size S which contains both of them, because for other S which doesn't contain them, these are same on both weights computation, so we don't have to compute. So we have to just do the computation, which is at most n to the k minus 2. And the number of edges are at most quadratic number, so the algorithm actually runs in big O of n to the k time. So this is one example of how we can turn a probabilistic argument into a deterministic algorithm, and this kind of technique is called de-randomization. But we can ask, what about local lemma? So if we have an argument using local lemma, can we turn it into an algorithm? Can you turn it into a deterministic algorithm, or maybe randomized algorithm? So if you think about this local lemma, turning it into a randomized algorithm is even not easy. So let's forget about deterministic algorithm. We just want to find one randomized algorithm for the case of local lemma. So let's say there is some problem, and you use local lemma to show that if you randomly choose, then with a positive probability, we obtain a desired solution. But oftentimes this positive number is actually very small number. Let's say problem of size n, and here the probability that you actually get what you want might be exponentially small. Probability e to the minus n. Let's write it this way. Then what do you have to do? You randomly choose all the things, then with probability 1 minus e to the negative n. That's not what you want. So you have to do it again. If you do, say, exponentially many times, then one of those times you will actually get the right answer. So you will get the desired solution. But this is not efficient. You have to do it exponentially many times. So, if you want to find a more efficient algorithm, it's not clear how one can even, convert the argument of the local lemma into an algorithm. But in 2009, Moser, and later in 2010, Moser and Tardis together find a way to construct find a simple randomized algorithm which can be applied to most of the applications of local lemma. So to learn about that, let's consider this setup. So this can be applied to many applications of local lemma, and those are kind of following the this setup. So let's say there are finite set, and for each element there we let C of B denote a random variable, and they are mutually independent. So, for example, we use the local lemma to prove a bound on Ramsey number. There, we consider that all the edges we color with either red or blue. And here, how we color each edge are, random variable. They are mutually independent of each other. So how we color this edge and how we color this edge and this edge are not dependent at all. But the bad events are dependent on each other. And these bad events are actually determined by the collection of this independent random variable. So let I be an index set, and for each alpha inside of I, there is a set A alpha, which is a subset of this omega, and an event, say bad alpha, which actually depending on how this C of B came out in this set alpha, A alpha. So, in this setup, of Ramsey number, for example, so each of these event or coloring edges are C, B, where B, so here B might be not a good way, so let's say E. So omega is edges of Kn here, and E is each element. Then C of E is a random variable which colors these edges by red or blue. And alpha is, say, set of size K. And A alpha is exactly the collection of edges inside of alpha. So alpha is set of size K, and then you choose all the edges here. For example, in here you can say that this is alpha. Then these three edges are forming A alpha. And bad alpha is the event that or CE is same with CE prime for E and E prime inside of A alpha. So event that these three edges have the same color. And let's say P of alpha as a probability of this bad event happening. And we let alpha and beta are depending each other or related. If they share when alpha and beta are in I, we say that they are related if they share some element together. So for example, if we consider this and this beta, then they are related. This related notion indicates whether the two bad events are dependent each other or not. In this case, they share this edge together, so they are dependent. So they are not independent. But if we have two sets here and here, which are edge disjoint, then those events are independent. So this is our setup. And many of our application of local lemma can be actually, rephrased using this setup. Now, what Moser proposed is the following algorithm, which is called Moser's fixed algorithm. So for each v in omega, we choose the COV at random. So, meaning that we have this Kn and we color the edges at random and pick. If no bad event happens, then we are happy. Otherwise, pick one arbitrary bad event, BAD alpha. Here, you can choose anything arbitrary, but if you want to make it more clear, then you give an ordering between bad events, and then you choose the, you choose the bad event which has the lowest, which has the most priority in the ordering. So just choose any arbitrary deterministic ordering, and then according to that ordering, you can choose the bad event. We choose the bad event among the all bad events happened. And now what we do is we select all the CV at random again. What it means is that in here, you have this bad event, red triangle. So what you do is you delete the coloring of them. And then now you redetermine the colors of each edge. It's these three things. For all these three edges. And what we do is we repeat this wire. There's bad events occurred. So in here now again there is this blue triangle and another blue triangle. You just choose one, this one, and you resample this. So we randomly color them again. And now again there is a red triangle. So we randomly color this again. Say blue. And again we have a blue triangle here. So we forget this and forget this, and we randomly say color again. Then now there is no red triangle or blue triangle, then we stop. So we just keep do this until we actually get the correct one. And now we want to claim that this actually, works with high probability, and this actually finishes in a finite time. And that finite time is, not too bad. So for that, we need to define some notation. So let's say let log be the sequence alpha 1, alpha 2, alpha u, where this alpha t is the alpha that we selected at this time. So in here we keep selecting this alpha and then we reshuffle them, resample them, and then we keep going. So this resampling might introduce new bad event, just like you saw it before. There was a triangle which was not monochromatic, but because we resampled this triangle, now this is no longer a monochromatic, but this might become monochromatic. But you don't care, you just keep do this. And while doing that, the choice that you make, you just record it. Then that's log. And once it's ended, then let's say that's time, terminal log, the length of log as u. So now what we want to do is so once we apply this algorithm, then we will get this log. And we want to bound the probability that specific log is obtained. So we want to show that this log is likely to have a short length or bounded length. For that, we want to show that if this log is too long, then it is unlikely to actually obtain that specific log. And then we want to add the probability of getting specific log for all long log. Then we can actually show that it is unlikely to get a too long log, so it's likely to be short. But how can we bound the probability of getting that? So let's consider this. Let's say these are the elements in omega. And initially there are some bad events happen. So these are the bad events, and you choose one. So you choose this one, and then you reshuffle them. So now this is no longer a bad event, because while reshuffle them, this has changed. So altogether here, this is not a bad event. And then, but these are still bad events, so you chose this. and then you reshuffle them. And now because of reshuffling, new bad event occurred. This is bad event. So this was previously not bad, but now bad. So now you choose this and then you reshuffle them. And now this is no longer a bad event. But this introduced, say, another bad event here. And another, say, bad event here. And you, say, reshuffle this. And then that's our fourth time. And then after reshuffle them, so this is still bad event, so you also reshuffle this. So if you consider this, in this case, I mean, so this set is 1, alpha 1, this set is alpha 2, this set is alpha 3, and this set is alpha 4. This set is alpha 5. Wait. 3. Then the probability of this event happen. So this specific, sequence is obtained. If you estimate such a probability, then what would be the way? So first, this has to be the bad event for alpha 1 must happen. So which happens with probability of alpha 1. And also, bad event of alpha 2 must happen. And those two are independent, so you can say multiply. And bad event of alpha 3 must happen, but is it independent of these two? So this must happen at the first initial configuration, and this must happen on the first initial configuration. And this must happen while these two are taken as first configuration, initial configuration, while this is kept as the first initial configuration, and these two are the not initial one, but the second random sampling. So this was fixed at the initial one, and then because this was bad, you actually sample these two again, so which are sampled on the second round, but this was sampled on the first round. So with this combination, this bad event has to happen. Such event happen with probability p alpha 3, but this depending on second round sampling and first round sampling, and these depending on first round sampling and first round sampling. So first round sampling of this and second round sampling of this are actually independent. It's like pair coin. If you flip first time and flip second time, they are independent event. So we can actually consider that's also independent. And again, this you consider third round sampling and first round sampling. That determines this 4. And that determines this, again, 5. So we want to claim that this actually upper bounds the probability of getting specific log. Here, we ignore these bad events, because this bad event is actually not independent with this. And this bad event is also not independent with, say this third one, because this third one uses this first sampling of this, and this bad event also uses first sampling of this. But so if we multiply this to here, this to here, then that doesn't give us any upper bound, because that's not independent with this event. So we just forget that, but still we can get the upper bound of this. And these bad events doesn't, it's not really related to the log anyway. So we want to estimate this probability. But this is not the end. Remember, we want to bound the probability of getting this specific log also, but we want to sum them. We want to consider all possible log sequence, and then we want to sum the probability so that later we show that the probability of it become too long is small. So we also want to figure out which kind of sequence can also arise. So here, this is first bad event, second bad event, and because of this second bad event, third, fourth, fifth are there. So because of this and because of this, next one can be like activated. So somehow, I mean, you can consider this as there is one thing, one event, and this activates several other events, and this could, I mean, activate several other bad events, and so on. This is something like a tree-like structure. To be more specific, it's forest, because this is first event and second event, and from first one, nothing has branched out. So, I mean, motivated from that, we can define the following concept of model tree. And this will help us to actually analyze, I mean, what kind of sequence we can get. And then for those sequence, we consider this kind of probability of getting those log sequence. And then we can sum them and then we estimate them. Let's say the depth of a vertex in a rooted tree is its distance. Rooted tree is a tree with a root vertex. So in a tree, you designate one vertex as root. So distance from the root is depth of a vertex, and the depth of entire rooted tree is the maximum depth of its vertices. And a model tree is a finite rooted tree T equipped with a labeling satisfying the following. If U with label alpha is a child of V with label beta, then alpha and beta are related. And if U has label alpha and V has label beta with related one, then U and V has different depths. So such a model tree T equals with this F, we let P of T be the summation of all P value on the labels of vertices. So remember, this F is to I. So for each element in I, we have this probability. So for some technical reasons, so here, I mean, I actually, consider that you have 1 and you have 2, and then 2 from you have 3, 4, 5 are branched out. But then you might think that it's more intuitive to consider these as root, and then these are the, things below. But it's actually we will, consider it in an inverse way. So from the later, so 5, 4, 3, 2, 1. That's how we will start, considering. So you have 5, and then 5 and 4 are related, and 4 and 3 are related, and 3 comes from 2, and 1 is as its own. So this is some kind of rooted tree that we want to consider. And here, if you see, you can kind of see why we consider these two conditions. So if you have 5 here, and then 4 is actually the reason why we get 5, because of shuffling of 4 makes the 5 happen. That means there should be some common element here, so they have to be related. So that's where it comes here. And the second one is that if 2 are related, then they have to be at different depths. That's related to how we get this multiplication. So 2 and 3 are related, but in here 2 are using the first round sampling, and 3 are using the second round sampling and first round sampling. So we want to make sure that they are like disjoint. So that's also kind of related to this definition. Anyway, so that motivates this definition, and then we will later see that what we will do is for each log sequence we will define a module tree, and then show that for different log sequence you get the different module tree. And then we want to bound the summation of this probability of sequences, and we want to consider the corresponding summation of this number, this probability for all module sequence, and then we want to bound them all together. So that's what we will do next time.